And I just did a calculation this morning. You are the first one to hear that the object will come closest to Jupiter on March 16th, 2026. And it will arrive exactly at the right distance to Jupiter, to within a small fraction of a percent, exactly the right distance, where the gravity of the sun will not be able to tear apart any probe that it releases near Jupiter. So it arrives just at the right distance so that Jupiter's gravity will overcome the sun's tidal gravity, and anything it releases there will stay there, which suggests why did it arrive exactly at the distance? In order perhaps to release some probes near that planet. So there are lots of questions. It also shed nickel with very little iron, lots of anomalies, and NASA did not discuss them. Instead of what they did, which is to say, we pretty much know that it's an object of the type that we have seen before. They should have emphasized the mysteries, or they should not have held a press conference because they didn't have much new information there.
On November 23rd, new analysis was released that added yet another anomaly to the growing list surrounding the interstellar object known as 3I Atlas. It was the 13th such anomaly identified since astronomers first began studying the object's peculiar behavior, and it immediately stood out as the most perplexing discovery so far. Unlike earlier anomalies, unusual rotation rates, strange light curves, non-gravitational accelerations, this one involved a level of mathematical precision that should not occur in a naturally evolving comet. It was the kind of precision that would be difficult to achieve even with deliberate engineering, let alone the chaotic and unpredictable processes of frozen rock and ice drifting through space for millions of years. Yet the numbers were unmistakable. At this moment, 3I Atlas is on a trajectory carrying it toward Jupiter. Its closest approach is scheduled for March 16, 2026, a date now etched into the timelines of observatories around the world. Less than 4 months remain before the encounter, and the astronomical community is already preparing for intensive monitoring during the window. Data has been flooding into NASA's Jet Propulsion Laboratory from more than 230 observatories across the globe, forming a comprehensive observational network dedicated to tracking the incoming object. These measurements have allowed scientists to calculate the object's expected distance from Jupiter at closest approach with extraordinary precision. The most recent figures place the encounter at approximately 33.21 million miles from the gas giant. What makes this number remarkable is how tightly it matches Jupiter's hill radius, the invisible gravitational boundary around a planet beyond which the gravitational pull of the Sun becomes dominant. Inside the hill radius, Jupiter's gravity can seize objects, draw them into long-term orbits, or at least significantly redirect their motion. Outside that boundary, the influence of the Sun is overpowering, preventing capture. The hill radius is not an estimate, nor is it merely a conceptual tool. It is a calculated value derived from exact physical parameters: the mass of Jupiter, the mass of the Sun, and the precise positions and velocities of both objects in their mutual orbit. For the specific date of March 16, 2026, the calculated hill radius for Jupiter is approximately 33.24 million miles. The difference between this theoretical boundary and the predicted path of 3I Atlas, only about 35,000 miles. In the context of a 33 million mile distance, this deviation is so small that it amounts to a hit on the boundary to within 0.1%. Statistically, the likelihood of an interstellar object randomly passing this close to such a gravitational threshold is extraordinarily low. Calculations suggest a probability of roughly 0.004%, around 1 chance in 26,000. To put that into perspective, even deliberate spacecraft targeting maneuvers conducted by teams of engineers using carefully planned burns would struggle to achieve such accuracy on a first attempt. The fact that a natural object, influenced only by gravity and whatever internal processes it carries, appears to be on track for such a precise pass has raised significant scientific debate. The mystery deepens when considering the non-gravitational acceleration detected in the object's motion motion. Observers monitoring 3I Atlas earlier in its journey through the inner solar system noted that its trajectory was deviating slightly from the path predicted purely by gravitational interactions with the Sun and the planets. These deviations were subtle but measurable, quantified as an acceleration of approximately 5 times 10 to the -7th astronomical units per day squared. At face value, that number may seem obscure, but its implications are significant. It indicates that some force, other than gravity, was acting on the object, altering its motion by a measurable amount. Such non-gravitational forces are not entirely unfamiliar in comet studies. As comets approach the Sun, volatile materials within them warm up and sublimate, producing jets of gas and dust that escape from their surfaces. These jets act like natural thrusters, imparting small but detectable impulses that can shift the comet's trajectory. But natural outgassing is inherently chaotic. The location of volatile pockets, the orientation of the comet's rotation, the distribution of sunlight across its surface, all these variables contribute to a messy, unpredictable pattern of jet activity. For outgassing to push a comet by exactly the amount needed to redirect it by 62,000 miles, the difference between its original path and its current trajectory near Jupiter's hill boundary would require a level of precision that would be extremely unusual for a naturally active body. Nonetheless, the acceleration measured in 3I Atlas produced exactly that trajectory shift. The object's path was altered just enough to guide it from where it would have been heading naturally to a course aligned with the invisible threshold around Jupiter. Even if one assumes a highly active comet with strong jets, hitting a gravitational boundary to within a few tens of thousands of miles across millions of miles of travel remains an extraordinary coincidence. The relevance of the Hill radius extends beyond gravitational capture. Sitting along this boundary are the so-called Lagrange points, regions of space where the gravitational pull of Jupiter and the Sun balance in such a way that an object can remain stable with minimal energy expenditure. These points are invaluable for spacecraft designers. Missions such as the James Webb Space Telescope are positioned at Earth-Sun Lagrange points to take advantage of the stable environment and low fuel requirements. Around Jupiter, similar points could theoretically serve as staging grounds or observation points for long-term scientific instruments or other structures.
For an interstellar object to arrive at exactly this range, following a path adjusted by non-gravitational forces, has prompted speculation about its nature and origin. While the idea of intentional course correction remains outside the mainstream consensus, it is not dismissed entirely by some researchers. Avi Loeb, a physicist at Harvard University, known for exploring unconventional explanations, points out that the statistical improbability combined with the measured acceleration warrants consideration of all possibilities, including the presence of a propulsion mechanism or other engineered feature. In Loeb's interpretation, the object may have made deliberate micro-adjustments, steering itself toward a region of gravitational stability around Jupiter for reasons unknown. However, the lack of direct evidence for artificial origin remains a major obstacle. No radio signals have been detected coming from the object, no thermal signatures have been recorded that would indicate waste heat from an engine or internal system, and no visible structures or emissions have been found. To date, the only anomalies are the trajectory, the acceleration, and the statistical unlikelihood of the configuration. As scientists often note, extraordinary claims require extraordinary evidence, and none has emerged yet that would definitively support a technological explanation. Other possibilities are being explored with equal rigor. One is that the calculations regarding the object's orbit may still contain slight inaccuracies. Even with hundreds of observatories contributing data, small uncertainties remain. A tiny unaccounted-for gravitational influence, perhaps from an overlooked mass distribution or an unusual interaction with solar radiation pressure, could theoretically shift the object's predicted path. If the initial trajectory estimates are off by tens of thousands of miles, then the observed alignment with the Hill radius could be an illusion created by incomplete modeling. Refining these calculations is one of the main priorities as the object approaches Jupiter. Another explanation gaining consideration is the possibility of exotic comet physics. While natural outgassing is generally chaotic, not all comets behave in predictable ways. Interstellar comets in particular may contain volatile materials or structural characteristics never before observed in solar system comets. If 3I Atlas possesses an unusually uniform distribution of volatile materials or an internal structure that channels sublimating gases in a stable direction, then its non-gravitational acceleration could be far more consistent than typically observed. This would allow outgassing to act in a controlled manner, inadvertently producing a trajectory shift that happens to intersect precisely with Jupiter's Hill radius. Such a discovery would expand the understanding of comet evolution beyond the solar system, rewriting assumptions about how interstellar bodies are shaped and behave during their long journeys through space.
A third explanation, embraced by the majority of astronomers, is simple coincidence.
Over billions of years, countless interstellar objects have passed through the solar system, even if only a few have been detected due to limitations in observation technology. In such enormous time spans and with such large numbers, statistically improbable events can and do occur. Just as lightning occasionally strikes the same place multiple times, or meteorites occasionally fall with remarkable precision, a single interstellar body passing near a gravitational boundary by chance is not impossible. The fact that 3I Atlas is only the third interstellar object detected does not necessarily reflect reality, only the limits of current detection methods. If millions of similar objects have passed unnoticed, then one random alignment with Jupiter's Hill radius is not unreasonable. Even so, the coincidence explanation leaves open important scientific questions. If the trajectory is random, why is the non-gravitational acceleration so precisely aligned with the required shift? Why did the object's path deviate in exactly the direction needed to close the gap? And why, among the few objects finally detected, is such a statistically rare event occurring now, with one of the earliest interstellar visitors that modern astronomy has been able to study in detail? These questions drive continued interest in the object and the upcoming close encounter with Jupiter. Regardless of which explanation ultimately proves correct, the case of 3I Atlas is scientifically valuable. If the event is a coincidence, then astronomers have witnessed a statistical outlier of extraordinary proportions, a reminder that rare events can and do occur in a universe governed by probability. If natural cometary behavior is responsible, then new models of interstellar comet physics may emerge, potentially refining the understanding of how such objects are structured, how they evolve across vast distances, and how they interact with starlight and planetary atmospheres. If the calculations contain errors, resolving those inaccuracies will improve predictive models for all future interstellar visitors, enhancing humanity's ability to track and characterize objects from beyond the solar system.
And if, however unlikely, any technological explanation emerges from future data, the implications would be profound. The detection of even a single engineered structure entering the solar system from interstellar space would represent one of the most significant discoveries in human history, reshaping scientific and philosophical perspectives alike. For now, there is no proof of such a possibility. Only trajectories, accelerations, and anomalies that encourage cautious curiosity. As the approach to Jupiter draws nearer, observatories are preparing for a flood of new information. Additional observations will soon refine the object's path to an even greater degree of precision, narrowing down the sources of its past deviations and revealing whether the alignment with Jupiter's Hill radius is tightening or drifting. Data gathered during the March encounter will be pivotal. Gravitational interactions with Jupiter will either confirm the object's expected path or produce new deviations that shed light on the underlying processes steering it. Over the next several months, astronomers anticipate that increasingly detailed measurements will help determine whether 3I Atlas is a natural comet behaving in an unexpected way, the product of an error in orbital estimation, a statistical rarity, or something more complex. No matter the outcome, the object's trajectory has already sparked one of the most intriguing scientific puzzles of recent years. Its arrival at Jupiter's boundary carries with it the potential to deepen understanding of interstellar visitors and challenge assumptions about the quiet regions between stars. The scientific world now waits for the moment of closest approach, when data and physics will reveal whether 3I Atlas is an improbable outlier, an exemplar of unknown cometary behavior, or the first sign of something that defies the familiar patterns of the solar system.